Hi everyone, my name is Ohad. I'm a PhD student at Yaron Bromberg's group at Hebrew University. And in this talk, I'm going to describe our recent work on quantum information processing of spatially entangled photons using a programmable light converter. And I would like to begin with a brief motivation for our study, which lies in the field of quantum information processing. And really, in recent years, many applications in quantum information processing have been developed, for example, measurement-based quantum computation and quantum cryptography. And what is common to all of these applications is basically that their photonic implementations require three main building blocks. First, you need a source to generate a single or entangled photons, etc. Then you need to find a way to manipulate the photon, for example, to encode information or perform some computation. And finally, of course, you would like to detect the photons to read out information or the result of your application. In this talk, I'm going to focus on the manipulation building block, and I'm going to describe our approach for manipulating and performing unitary transformations on entangled photons using something called a multiplane light converter, which I'm going to describe in more detail shortly. But before I get into the details, let me set the baseline by describing what will be an ideal photonic quantum processor. So I've listed here a number of requirements from such an ideal processor, and we'll go through them together using the example of photonic integrated circuits, which are usually considered as the leading candidate for implementing such a quantum processor. So a photonic integrated circuit is basically a large mesh of beam splitters in blue here and phase shifters in red, and that connects a set of n input waveguide modes, in this case 12, to a set of output waveguide modes. And using this beam splitter and phase shifters, we can actually program any unitary transformation between the input and output modes. That's why I call these integrated circuits a universal, in the sense that by programming the different phase shifters, we can encode any unitary transformations. It can be made quite low loss after great progress in this field. And it's also very compact, as you can see in this beautiful picture. However, the scalability of such devices is challenging, to say the least, as you will need something on the order of n squared elements in order to implement an n by n unitary transformations, which really limits the number of modes that you can control to tens of modes at most. So the scalability of such devices is limited. And of course, this platform is very far from being more generic, in the sense that the input and output modes are fixed and are determined by the waveguides. And for example, if we look at applications such as entanglement distribution through a multimode fiber, then the most natural set of modes will be the modes of the multimode fiber, and we'll need to add components to our system so that we can use these integrated circuits. In this talk, I'm going to describe our approach for processing quantum information, and we would like to use something called multiplane light conversion, or MPLC in short. So what's MPLC? Basically, it allows us to perform unitary transformations on spatial modes of photons using a cascade of phase masks separated by free space propagation. So here you can see an illustration from a company named Kylabs that actually sell these products commercially. So using an optimized set of phase masks, we can transform the input and output modes at the desired fashion. And of course, in the experiment, we don't need to have such a large cascade. We can simply use a multipass cavity and bounce the light back and forth between a spatial light modulator that can encode and imprint any phase that we want on the photons and the mirror. So using this multipass cavity and MPLC, let's go back to our requirements from an ideal photonic processor, and let's see how the MPLC is doing in this respect. So first, this approach is indeed universal and programmable in the sense that by programming the phase on the spatial light modulator, we can encode any unitary transformation between the input and output modes, given that we had enough planes or phase masks. It's low loss and it's rather compact, but of course not as compact as integrated circuits. However, the scalability here is believed to be better because we only need something on the order of n phase masks and planes to really encode a general unitary transformation. And often for some applications, as I'm going to show you on the next slide, we can get away with much less planes. Of course, this approach is also more generic, which is very nice, because we are not limited to the modes of the waveguides. We don't have any waveguides here. We simply can program the phase mesh to really correspond to any set of modes that we choose. So just an example of the power of this multiplane light converter in the classical domain. So here you can see an example by the group of Joel Carpenter, a really beautiful work, where using only 7 planes in a multiplane light converter, they were able to sort out 210 Gaussian modes into spatially separated Gaussian spots. And they recently improved it, and using 14 planes, they could control over 1,000 modes. So comparing to something on the order of 10 modes that is possible with integrated circuits, this could be an interesting tool. And indeed, people have used it also for the quantum domain. So the group of Robert Fickler, they used, for example, MPLCs to perform unitary transformations on single photons, and also to study two-phone interference of photons in the orbital angular momentum degree of freedom. However, we know that for quantum applications, entanglement is a crucial component, and our contribution was to really develop a multiplane light converter and show that it can transform and really process entanglement as well. So this is basically our scheme. We have at the input a pixel entangled state, so a 2-photon state that is entangled in the spatial degree of freedom. We then pass this entangled state into a multiplane light converter, and finally, of course, detect the correlations, the output, to see that we indeed succeeded in implemented our unitary transformations. So in the experiment, we have a spontaneous parametric down conversion source, an SPDC source that creates these spatially entangled photons. And the photons then go into a 5-plane multiplane light converter. And we really see this entangled state and how we can transform it. So in the next few slides, what I'm going to show you is the results of our experiment. And basically, we want to demonstrate the power of MPLC as a tool for quantum information processing. So using the same setup, the same hardware, we simply reconfigure the phases on the SLM, on the spatial light modulator, to perform different tests that are important for quantum information processing. So the first test that we consider is high-dimensional entanglement certification. So for n equals 3, so a 3-dimensional entanglement in the input space, we want to certify that the input state is indeed entangled. So we use the MPLC to transform between 2 measurement bases. So first, we measure the correlations at the standard computational basis. So the MPLC simply encodes the identity operation, and we measure nice correlation between the photons. And then we transform to the discrete Fourier transform basis. So the MPLC implements the DFT matrix on each of the photons, and we measure correlations as well. It enables us to show that the fidelity of our state is over 90%, and certify that we indeed have a 3-dimensional genuine entanglement. And we can then use the programmability of our MPLC to also play with the different relative phases in our state. So we have this highly entangled state, and we can use the MPLC both to change the measurement basis to the DFT basis and to control the relative phases phi1 and phi2 between the different terms. So here you can see the correlations between different modes at the output of the MPLC as a function of the phases phi1 and phi2. And you can see that we have this controlled quantum interference with a great agreement between experiment and theory. Another thing that we can do is to test the universality of our MPLC device. And to do so, we considered random transformations. So we wanted to really implement random transformations on 4 spatial modes. So we experimentally implement 400 such random transformations and look at the fidelity of the outputs coincidence detection compared to the theoretical expectation. And we get a fidelity close to 90%. And the fidelity here is basically limited by the number of planes, MPLC planes that we use. So in the experiment, we have only 5 planes, and we get a fidelity near 90%. And in blue here, you can see what we expect from numerical simulations. So if you simulate our device, we get that the experiment is very close with the simulation. But if we go to still a moderate number of planes, for example, 10 planes, we can get to really high fidelities on random transformations. The last thing I want to show you is how we can use the MPLC for mode conversion, for example, for entanglement distribution. So as I've told you, the MPLC device is more generic. So if we have entanglement at the input in the pixel basis, so we have this correlated spots, we can perform the identity operation on one of the photons, but we can transform the other photons from this pixel basis into the mode basis of a multimode fiber, namely to the linearly polarized 0,1 and 1,1 modes. So now at the output of the MPLC, we can measure the correlations between the photons as well and see that their spatial profile can be either the LP01 mode or the LP11 mode, depending on which spot you measure. So we can convert the modes and convert the entanglement so that it could be later distributed, for example, through a few mode fiber. So to sum up, we believe multiplane NAT conversion is really a promising candidate for quantum information processing due to its possibly better scalability, universality, etc. And we demonstrated the use of MPLC for the first time for processing entanglement photons and entangled photons and entanglement. And we performed high-dimensional entanglement certification, controlled two-photon interference. We performed high random unitary transformations with quite a high fidelity, and also mode conversion, really showing the promising results of the MPLC platforms. So thank you very much for listening. Unfortunately, I couldn't participate live because I'm on my honeymoon currently. And so this is a recorded talk, but you can look at the archive for more details, and please email me if you have any questions. I'll be happy to answer. So thank you very much.